When the universe began, it wasn't filled with planets or stars. It was an unimaginably dense, blindingly hot shockwave of pure radiation. As that raw energy cooled, it should have condensed into identical pairs, one particle of matter and one of antimatter. But the moment they touch, they annihilate each other, instantly converting back into pure energy. If this symmetrical cycle of creation and destruction had played out flawlessly, the two sides would have perfectly canceled each other out, leaving absolutely zero physical mass behind. A cosmos made of perfectly balanced pure light has no building blocks. You cannot form galaxies, planets, or human beings out of empty radiation. Yet when we point our instruments at the sky, an empty cosmos isn't what we see. We live in a universe packed with physical stuff. What we don't see, anywhere in the observable universe, is primordial antimatter. It is practically non-existent. The math suggests exactly what happened. In the extreme heat of the early universe, for every 1 billion antimatter particles that were created, there were exactly 1,000,000,001 matter particles. That microscopic surplus, a single extra particle of matter out of a billion, is the only reason anything survived the Great Annihilation. Physicists call the process that forced this imbalance Baryogenesis. Every single atom in your body, the Earth beneath you, and every star you see is simply the leftover debris from that cosmic rounding error. In 1967, the physicist Andrei Sakharov realized that for us to exist, the infant universe had to break its own rules of perfect symmetry. He proposed 3 strict conditions had to overlap at the exact same moment to trigger baryogenesis. This diagram shows the first rule, baryon number violation. Normally, particles interact keeping the total number of baryons constant. But at extreme temperatures, quantum anomalies force an unequal conversion, creating more matter particles than antimatter ones. The second requirement is a violation of charge and parity symmetry, or CP symmetry. This rule dictates that if you swap a particle for its antimatter twin and flip its spatial directions, it should behave identically. Breaking this symmetry means matter and antimatter operate slightly differently. Certain heavy particles will decay into regular matter just a fraction of a second faster than they decay into antimatter. Experimental physicists like Chien-Shiung Wu conducted experiments proving that these deep symmetries can be broken in the real world. Without these two broken rules, equal amounts of matter and antimatter would have remained perfectly locked in a mutual suicide pact. But there is a problem. This rapid expansion stayed uniformly hot and stable. These rule-breaking reactions would eventually run in reverse, canceling out any matter advantage they had created. That brings us to Sakharov's third condition, a departure from thermal equilibrium. The universe could not stay in a steady state. It had to be expanding and cooling violently fast. This rapid expansion stopped the reactions from reversing. This freeze-out permanently locked that tiny 1 in a billion matter surplus into reality. As the cosmos continued to cool, the remaining billions of perfectly matched pairs collided, wiping each other out in a blinding flash of background radiation. That singular, isolated extra particle, protected by the expanding freeze-out, was the mechanism that allowed the physical universe to coalesce. We know these 3 conditions are physically required for us to be here, but current mathematical models fail to explain our existence. This graph plots the ratio of antiprotons to protons measured in cosmic rays. When we map observed data like this against the standard model of particle physics, the known asymmetry between matter and antimatter is roughly 10 orders of magnitude too small to explain the amount of matter we observe. This massive deficit means the widely accepted standard model of particle physics is incomplete. To bridge this gap, researchers are searching for unmapped physical laws. They use massive, complex particle detectors to test exotic theories like mesogenesis, where dark matter might be siphoning away the antimatter. The origin of our matter remains an unexplained phenomenon. Our entire existence hinges on laws of physics, still hiding in the cosmic margin of error.